The last group in this session has students from chemistry, or researchers in chemistry that span the academic rank. And so we have Kristine Arquero, who is a PhD student, will defend very soon, very excited to go to her defense. Veronique, Perraud, who is a project scientist, and they're both in the Fillets and Tips group. And then Jing, who is a postdoc in the Gerber groups.
As we've learned already this morning, Los Angeles is a megacity known for its air pollution. In fact, when we open our windows, it often looks like this. This is the infamous Los Angeles smog. But it doesn't always look like this picture. Actually, some days we can see the skyline and the mountain on the background. So what is it that makes those two pictures so different? Well, in the first one, we actually see the results of the chemistry happening in the atmosphere, converting gases into low volatility species that condense and form particles. Those particles are big enough, they scatter light and leave such a hazy view. How those particles form in the atmosphere is a topic of our research. In air, most new particle formation events have been associated with gas-phase sulfuric acid. But sulfuric acid never truly condenses on its own. It's usually combines with water and amines to form small clusters that will grow by uptake of more molecules to become particles. Sulfuric acid originates from the photooxidation of another gas molecule, sulfur dioxide, or SO2. SO2 is a molecule that is emitted directly into the atmosphere, largely from anthropogenic sources such as power plants and industrial ships. But a small fraction of that SO2 actually comes from the photodegradation of other gas molecules that contain 1, 2, or 3 sulfur atoms in their backbone. We dub those compounds organosulfur compounds. When those compounds are oxidized in air, they form another key molecule, MSA, or methane sulfonic acid. MSA is structurally similar to sulfuric acid, and thus it will be able to part in the same reaction as sulfuric acid, combining with amine and water to form particles. Yet this entire chemistry is not well understood, and this is where we come in. First, we needed to understand how important those organosulfur compounds are in the air around us. This is a map of the South Coast Air Basin of California. So where in this area those organosulfur compounds could come from? What we know is that phytoplankton, which are microorganisms living in the ocean, are able to emit a lot of those compounds above sea level and along the coast during phytoplankton bloom. What we don't know is the spatial distribution of those compounds inland. So, in the collaboration with the break group here at UCI, we took our instrument into the field and we wanted to know where were the sources for those compounds. Turns out that it's in Chino, an area with intensive agriculture and livestock activity, that we measure lots of those compounds in air. Interestingly, during the same field measurement, we also measure lots of amines. So you can already see that the precursor for particle formation coexist in the atmosphere. If we go back to our original scheme, we know the first step very well, the conversion between organosulfur compound to MSA. There is a missing link. It is if and how MSA form particles by combining with water and amines. And this is the reason why we need the supports from laboratory control experiments.
So MSA and amines coexist in air, but do they react with water to form particles? To study this reaction in situ is challenging because the atmosphere itself is a complex chemical reactor. So with the help of field measurements, we can design a laboratory experiment. And in the lab, we can create a controlled atmosphere to study if MSA reacts differently with different amines. So we chose 2 different amines, both of which were measured out in Chino. We have MA, or methylamine, and TMA, trimethylamine. MA is a primary amine. It has 3 opportunities to connect to other molecules via hydrogen bonds. TMA, a more basic amine, is a tertiary amine and only has 1 opportunity to connect to other molecules via a hydrogen bond. And we expect hydrogen bonding to be an important interaction between gas-phase amines, water, and MSA to form particles and then grow to sizes that we can detect. Now, is it the basicity, the structure, or the opportunities to hydrogen bond that will affect an amine's reactivity with MSA? Well, before we get into the results from our experiments, let's take a closer look at where we do this experiment. This is our looking glass float system in the lab, and over here is where the gas phase reactants enter. They're allowed to react along the length of the flow tube, and at the other end, we have any particles that are formed sent to detectors. If we take a closer look at this system, we have a sampling line that moves along the length of the flow system so that we can monitor this reaction as a function of time. And the gases enter through the inlets on the other end. And when the gas phase amines, water, and MSA meet each other, they form particles, and a fraction of them are sent to the detectors at the other end. And even though our system is all glass, actually the particles we form are just nanometers in size, so they're too small to scatter light and we can't see them. So we rely on our detectors to count and size the particles for us. So let's see what we found in the lab. And again, how that works. With MSA and water only in our system, we don't form a significant number of particles. And if we add just a little bit of MA, we form a ton of particles. Now let's repeat this experiment with TMA instead, and we don't form any particles at all. So already we see MA is more efficient at forming particles with MSA and water. In fact, we have to add 75 times that amount of TMA to get a comparable amount of particles that just a little bit of MA needs to form. So what is this difference? Well, unfortunately, we're limited by the detectors in our lab that can only see particles larger than 3 nanometers. So we turn to our theoretical chemistry colleagues to help us get a better look at what's happening at the molecular level.
Veronique and Kristine have introduced the particles from regional scale to the nanoscale. In the process of new particle formation, the gas reactants usually form small clusters first, and then grow to the larger particles. At the molecular level, we can calculate the most stable structures of these small clusters. Through analyzing the structures, energies, and properties, we can better understand the mechanism of the new particle formation and growth. Here, we take the reaction of MSA, amine, and water as the example. In the most stable structures of MSA and water, MSA connect with water through forming 2 hydrogen bonds. Then we add 2 different amine to them. We found, no matter adding MA or TMA, the acid MSA always transfer 1 proton to the amine. So the proton transfer reactions between the acid and the base may be used to explain the experiments why adding amine to MSA and water can form more particles. Experiment results also show MA is more efficient than TMA in forming particles with MSA and water. In order to form same number of particles, 75 times more TMA are needed. Why MA and TMA is so different? So we compared the most stable structures of them, and then we found, for the TMA system, TMA just connect with the MSA and form only 1 hydrogen bond. That means, once TMA was bonded with 1 MSA, it's hard for TMA to connect with other MSA. But MA is much different. MA can form 3 hydrogen bonds with MSA and water. Besides 1 MSA is bonded with MA, 2 hydrogen atoms of MA also can form hydrogen bonds with other MSA. So MA has more opportunities than TMA to react with more MSA and grow the clusters. This may be the reason why we need less MA in the experiments. Through comparing the theoretical calculations on small clusters with the experiment result, many useful correlations can be found. This not only can help us understand the experiment more deeply, but also can predict useful information for the future modeling studies.
Once we have all the information, the spatial distribution of the organosulfur compound and the fundamental understanding on which species combine and how they combine, we turn to our colleague over at the engineering department. We give them those information that they can use as input into their 3D airshed model. that they can use to assess the impact of that chemistry on a regional scale. Here is an example of a model run that shows where MSA would be produced based upon the organosulfur compound emissions and the chemistry that we know so far. From there, they can run what-if scenarios, testing various policies and regulations to see which one will have the greatest positive impact on our air quality. In conclusion, in our research, we look at the MSA chemistry and how it is linked to new particle formation events in the atmosphere via different looking glasses. We start our journey on a regional scale with the field measurement of the particle precursor, which are the organosulfur compound that ultimately would lead to MSA in the atmosphere. From those gases present in the atmosphere to new particle formation events, there is a gap that only laboratory controlled experiment can fill.
So field measurements inform our experimental design, and in the lab we can investigate new particle formation in a very controlled manner, but our results are limited. But thankfully, our theoretical calculations can probe where we cannot see.
Through theoretical calculations, the gap between nanosized particles and small clusters can be decreased. Theoretical calculations on small clusters not only can provide new insights into the particle formation and growth, but also can predict the useful information for the future lab and modeling studies.
With the fundamental understanding of the chemistry behind particle formation from MSA, amine, and water on a molecular level, we can zoom back out to the regional scale and assess the impact of that chemistry on our air quality. We like to view this approach as the strength of our research, to look at one problem, not from an isolated perspective, but combining our approaches to be able to propose solutions on a broader level. Thank you.